ಎಲ್ಲರಿಗೂ ಹಾಗೆ ಮಾತಾಡೋಣ ಸರ್. ಎಲ್ರಿಗೂ ನಮಸ್ಕಾರ. ನಾವು ಕಳೆದ 3 ವರ್ಷದಿಂದ ಸೈನ್ಸ್ ಸಂಜೆಯನ್ನ ನಿರಂತರವಾಗಿ ನಡೆಸ್ಕೊಂಡು ಬಂದಿದ್ದೀವಿ. ಈ ಸೈನ್ಸ್ ಸಂಜೆ ಕಾರ್ಯಕ್ರಮದಲ್ಲಿ ನಮ್ಮ ಉದ್ದೇಶ ಏನಪ್ಪಾ ಅಂತಂದ್ರೆ, ಎಲ್ಲೆಲ್ಲಿ ಏನೇನು ಸಂಶೋಧನೆಗಳು ನಡೀತಾ ಇದೆ ಅದರ ಬಗ್ಗೆ ಒಂದಷ್ಟು ತಾಂತ್ರಿಕ ವಿಷಯಗಳನ್ನ ನಿಮಗೆ ಕನ್ನಡದಲ್ಲಿ ಅಥವಾ ಇಂಗ್ಲಿಷ್ ನಲ್ಲಿ ಮಾಡ್ಬೇಕು ಅಂತ ಯೋಚನೆ ಇದೆ. ಪ್ರತಿ 3 ತಿಂಗಳಿಗೊಮ್ಮೆ ನಾವು ಇಂಗ್ಲಿಷ್ ನಲ್ಲಿ ಈ ಕಾರ್ಯಕ್ರಮಗಳನ್ನ ಹಮ್ಮಿಕೊಳ್ತೇವೆ. ಉಳಿದ ಹಾಗೆ ಕನ್ನಡದಲ್ಲಿ ಕಾರ್ಯಕ್ರಮಗಳಿರ್ತವೆ. ಕಳೆದ ಬಾರಿ ಬಹುಶಃ ನಾನಿರ್ಲಿಲ್ಲ, ಆದ್ರೆ ಸ್ಟ್ರೋಕ್ ಅನ್ನೋ ಬಗ್ಗೆ ಇಲ್ಲಿ ಒಂದು ಭಾಷಣ ಆಗಿತ್ತು. ಹೀಗೆ ನಮಗೆ ನಿತ್ಯ ಬದುಕಿಗೆ ಬೇಕಾಗಿರುವಂತಹದ್ದು ಹಾಗೂ ನಿತ್ಯ ಬೆರಗು ತರುವಂತಹದ್ದು ಎರಡೂ ವಿಷಯಗಳನ್ನ ನಾವು ಇಲ್ಲಿ ಪ್ರಸ್ತುತಪಡಿಸೋದಕ್ಕೆ ಇಷ್ಟಪಡ್ತೀವಿ. ಇವತ್ತಿನ ದಿವಸ ನಾವು ಖಗೋಳ ವಿಜ್ಞಾನ ಅಂದ್ರೆ ನಮ್ಮ ಕೈ ಅಳವಿನಿಂದ ಆಚೆಗಿರುವಂತಹ ಲೋಕದ ಬಗ್ಗೆ ತಿಳ್ಕೊಳ್ಳೋದಕ್ಕೆ ತಂದ್ಬಿಟ್ಟು ಇಲ್ಲಿ ಸೇರಿದ್ದೀವಿ. ಖಗೋಳ ವಿಜ್ಞಾನ ಅಂತ ಅನ್ನೋದು ಮನುಷ್ಯನ ಚರಿತ್ರೆಯಲ್ಲಿ ಬಹಳ ಹಳೆಯದಾದಂತಹ ಒಂದು ಅರಿವು ಅಂತನೋ ಜ್ಞಾನ ಶಾಖೆ ಅಂತನೋ ಮಾತಿದೆ. ಅದರೊಟ್ಟಿಗೆ ಇದು ಎಷ್ಟರ ಮಟ್ಟಿಗೆ ನಮ್ಮನ್ನ ಬಾಧಿಸಿದೆ ಅಂತ ಅನ್ನೋದಾದ್ರೆ, ಇವತ್ತಿನ ದಿವಸ ನಾವು ಆಕಾಶವನ್ನು ನೋಡೋದನ್ನು ನಿಲ್ಲಿಸಿದ್ರು ಕೂಡ ಅದರ ಪ್ರತಿಯೊಂದು ಅಂಶಗಳು ಕೂಡ, ಖಗೋಳ ವಿಜ್ಞಾನದ ಪ್ರತಿಯೊಂದು ಅಂಶಗಳು ಕೂಡ ನಮ್ಮನ್ನ ತಾಕ್ತಾ ಇವೆ ಅಂತ ಹೇಳ್ಬೋದು. ಭಾರತದಲ್ಲಿ ಖಗೋಳ ವಿಜ್ಞಾನ ಮತ್ತು ಖಗೋಳ ಶಾಸ್ತ್ರದ ಬಗ್ಗೆ ಹಲವಾರು ವಿಶಿಷ್ಟ ಸಂಸ್ಥೆಗಳಿವೆ, ಸಾಕಷ್ಟು ಸಾಧನೆಗಳನ್ನು ಮಾಡಿದ್ದಾರೆ. ಅಂಥದ್ರಲ್ಲಿ ಇಂಡಿಯನ್ ಇನ್ಸ್ಟಿಟ್ಯೂಟ್ ಆಫ್ ಆಸ್ಟ್ರೋಫಿಸಿಕ್ಸ್ ಕೂಡ ಒಂದು. ಅವರೊಟ್ಟಿಗೆ ನಾವು ಸಾಕಷ್ಟು ಕಾರ್ಯಕ್ರಮಗಳನ್ನ ಕೈ ಜೋಡಿಸಿ ಮಾಡ್ತಾ ಇದ್ದೇವೆ. ಈ ಸಂಸ್ಥೆ ಮೈಸೂರಿನಲ್ಲಿ ಒಂದು ಹೊಸ ಪ್ಲಾನೆಟೇರಿಯಂ ಕೂಡ ಸ್ಥಾಪಿಸ್ತಾ ಇದೆ. ಇನ್ನೊಂದು ಬಹುಶಃ ಮುಂದಿನ ವರ್ಷದೊಳಗೆ ನಿಮಗೆ ಆ ಸೌಲಭ್ಯ ಕೂಡ ನಿಮಗೆ ಸಿಗುತ್ತೆ. ಆಗ ನಾವು ಮನೆ ಒಳಗೆ ಕೂತ್ಕೊಂಡು ಆಕಾಶ ನೋಡ್ಬೋದು ಅಂತ ಅನ್ಕೊಂಡಿದ್ದೆ, ಹೊರಗಡೆ ಹೋಗ್ಬೇಕಾಗಿಲ್ಲ. ಆದ್ರೆ ಇವತ್ತಿನ ದಿವಸ ಈ ಖಗೋಳ ವಿಜ್ಞಾನ ಮನುಷ್ಯನ ಸ್ಥಾನಮಾನವನ್ನ ವಿಶ್ವದಲ್ಲಿ ಯಾವ ರೀತಿಯಲ್ಲಿ ಬದಲಿಸ್ತು ಅನ್ನೋದರ ಬಗ್ಗೆ ಒಂದು ಭಾಷಣವನ್ನ ಕೊಡ್ಬೇಕು ಅಂತ ಅಂದ್ಬಿಟ್ಟು ಮಿತ್ರರಾದಂತಹ ಶ್ರೀ ಡಾಕ್ಟರ್ ನೀರುಜ್ ರಾಮಾನುಜಂ ಅವರನ್ನ ಕೇಳ್ಕೊಂಡ್ವಿ. ಅವರು ಯಾವತ್ತೂ ಯಾವುದಕ್ಕೂ ಇಲ್ಲ ಅಂತ ಹೇಳಿದ್ರು. ಸೊ ಹಾಗಾಗಿ ತಕ್ಷಣಕ್ಕೆ ಬರ್ತೀನಿ ಅಂತ ಹೇಳಿದ್ರು. ನಾನೇ ಬರ್ತಿದ್ದೆ, ಮತ್ತೆ ನನ್ನನ್ನು ಕೇಳಿದ್ರು. ಡಾಕ್ಟರ್ ರಾಮಾನುಜಂ is the head of outreach program in Indian Institute of Astrophysics, Bengaluru, and he will be running around 6 laboratories under the IIA. He very often comes to Mysore and he loves Mysore, so that I know. And so today I invite Dr. Ramanujam to speak on the improvement of humans and astrophysics.
Thanks, Namaskar. I can speak very bad Kannada very confidently in the street, but not for astronomy talks. So very sorry, I will speak in English. I can use this one. Is it okay? Yes. Okay, right. So welcome everybody. The title is slightly strange. It's not a title of a typical science talk, and it's not going to be a science talk in that sense. It's a slightly different talk. I'm going to take things from astronomy, but talk more about lived experiences, a little bit of history, a little bit of philosophy, and venture into fields I don't know anything about. So I kind of give you indulgence for it. But before I start, I want to ask you, what did you think the title is about? Are there any guesses, or do you have your own thoughts about what do I mean by astronomy and successive dethronement of humans? What do you think? I'll ask you a few questions now. So I got to put it back. What do you think it is about?
Probably the perceptions what humans have about the astronomy, how it got changed over the period.
Correct. But dethronement means we are on the throne and we were taken out of the throne. So what do you think, yeah, please?
I also think that in a lot of aspects, humans are very anthropocentric. So they actually think they are able to play superior, as a superiority complex.
Right.
And I think if you only understand that we are part of the whole cosmos or universe, it's a dethronement of our ego to actually understand. who
Correct. So
we are.
that's definitely part of the talk. Successive dethronement. Yeah, please.
How it gave a competitive advantage to certain civilizations.
I would actually be talking about the converse of it in some sense. Yeah.
Well, nobody knows the vastness of the universe. My English is not good.
No, but please, you can also please no, reply in Kannada, and if I don't understand it, somebody translate. So please feel free to. Sure.
And around that sun, we are living on this planet and we think ourselves as intelligent.
Yeah. Correct.
So the vastness of
Yeah. So then that will be part of the theme. Are there any other comments? Yeah.
The continuing realization that we don't know much about vastness.
That's definitely true. There was one more hand here. Yeah. That's definitely part of the reason all of you are here, right? Yeah. Okay. So I was also looking for one particular phrase which nobody said. So astronomy, the talk is going to be how astronomy dethroned humans. Dethrone implies that we're once on the throne or at the center of all powerful, or we thought we're all powerful, and how the knowledge of astronomy or the results due to the research in astronomy took us away from the center. Right? So the decentering in some sense, decentering of humanity. Successive in the sense that we've been removed more and more away from the center as more and more discoveries are made in astronomy. And I'm going to spend half the time talking of the most important decentering of humans due to astronomy, which was the discovery by somebody 450 years ago. So Copernicus, right? So half the talk is going to be about the Copernican revolution, right? And the other half would be how astrophysics, since Copernicus has completed that project to an unimaginable level. Okay, so that's the rough theme of the talk. Is that all right? Okay, fine. So a little bit about my own institute. Sharma of course introduced. Sorry, the resolution of my laptop doesn't match the resolution of the projector, so it's a bit low res. I'm sorry. So the Institute of Astrophysics is in Koramangala in Bengaluru. I don't know if you've heard of it. One of us or visited us. And if I don't hold it here. Okay, perfect. Okay, sorry. We've been around since 1971 as an institution, but we trace origins back to 1796 when the British East India Company set up what is called the Madras Observatory in Madras, now Chennai. And from 1796 it functioned till 1899 when it was moved to Kodaikanal as the Kodaikanal Solar Observatory. Which then became the Indian Institute of Astrophysics in 1971. And in fact, last year we celebrated the 125th anniversary of the Kodaikanal Solar Observatory. Right. So this is our headquarters in Koramangala. If you come and visit us, it's basically an office building. One of our major pride and joy, of course, is you might have heard about our observatory in Ladakh in a place called Hanle. Can I take this one maybe? Shorter, but might be better. Okay, is this better? I think this is better. Okay, so we have an observatory in Hanle, which is the height of 4,500 meters above sea level. We also have the Kodaikanal Solar Observatory. There was a stamp released recently this year on the 125th anniversary. We have an observatory in Bengaluru, which is near Vaniyambadi, on halfway to Chennai, which is again an observatory with telescopes to look at the night sky. It has been around since late 60s. We have a technology center in Hoskote in Bangalore. Well, in Bangalore, outside Bangalore, depending on how you like the traffic. There we do three things. One, we remotely operate a telescope in Ladakh from Hoskote. We have a center which makes a laboratory which makes space telescopes, and the two space telescopes we have made which are functioning. One is the ultraviolet imaging telescope on Astrosat, which is just finished its 10th year of operation. And the visible emission line coronagraph on Aditya L1, which was launched 2 years ago. That is this t-shirt here. I'm doing a bit of advertising to study the sun, and that's been around for 2 years. We also have a center there to make telescopes on the international project we are a part, India is a part of. We also have a radio observatory in Bengaluru, again in Karnataka. And of course, the new latest thing which will be ready early next year is the Cosmos Mysuru Planetarium, which will be coming up at the foothills of Chamundi Hill. If you go to Chamundi Hills, you'll see a dome-like structure. That's us. There's a flyer outside about the planetarium. You can feel free to take it. There are stickers and badges, so please take a couple of them for people you know. So that's our institution. Okay, so now coming back to our talk, presumably, and I say presumably because I'm not an anthropologist, a long time ago, many thousands of years ago, when people lived in smaller clusters and our knowledge of the world itself was limited in geography, we thought that our immediate surroundings were probably the center of the world, or the conception of the world we had. Right? The conception of a world was limited by how much we could see or travel to or heard from other people and so on. And this was both a physical center. We probably thought that our village or our region was center of everything. Also a psychological center in the sense that we thought we were the most important people around as well, right? And this probably, we have anecdotal evidence from literature, etc., from many cultures that this is probably true, right? But as our local geography knowledge expanded, either through travel or from hearsay and so on, our worldview also expanded over time, right? One presumes this is true. And encompass not just our small region, but our neighboring kingdoms, maybe the ocean, the seas, things which lay beyond the sea, beyond the ocean, and so on. So then our worldview expanded, but still each culture had its own concept of our place in the worldview. And of course, it is possibly true that most people thought put us in the center. However, I would maintain that it was the sky which is always the farthest and the largest frontier. That was the sky was what inspired our imagination. Though we could travel, the sky was something which is untouchable, untravelable too, and also challenged us in the sense of trying to come up with a worldview which incorporated the sky and the things we saw in the sky, which will still make sense based on what we know around us, right? By the way, most of these amazing pictures are taken by my colleague Doji Amchok. He's the engineer in charge of the Ladakh Observatory, and he really takes pictures like this easily. Okay, so therefore, for thousands of years, and when people say astronomy is probably the oldest science, what you mean is that for thousands of years, you look at the night sky, you see things moving, and then you see patterns in the movement, and you would naturally try and figure out what those patterns were. And the reason we say astronomy is one of the oldest sciences. They looked at the sky and noticed, at least these four things, right? None of us do because we don't look at the sky anymore, like Sharma said. One is that every day things go around us, right? The sun and the moon, the stars go around us once a day. If you then account for that, you also know that the moon goes around us once every 29 days or so, right? You also know the sun goes around us once a year, roughly in the sky, and the planets also go around us in various different orbits. Each planet has its own orbit, right? There's something for thousands of years humans knew this by observation, and therefore the obvious and one could argue the legitimate conclusion is that since everything goes around us with various time scales, we are the center of everything, right? And everything rotates around us, and therefore, we are at the center. And in every culture, pretty much every culture, religion and philosophy kind of aided this understanding in their own way, as well as local culture and stories and so on. And so it reinforced the notion in some sense of our specialness, right? And this talk is going to remove that specialness from all of you, basically, right? So therefore, it reinforces if everything goes around, literally the universe goes around you. They say, oh, he thinks that the world revolves around him, but we literally thought it revolves around us, and therefore we are special in some way just by the fact of observation, right? And the sun, and therefore let's look at a bit more detail, right? So we know that everything goes around us once every 24 hours. It's not 20, it's actually 23 hours for 6 minutes, but the 4-minute difference we will leave aside for the minute. And this defined a day, right? So that our concept of a day, which defines everything in our life, our quotidian life, is defined by the sky, right? And if you look at and therefore the entire universe, was consisting of everything you could see in the night sky, also went around us once a day, and the sun also went around us once a day, and it also gave us light and heat. So it looked like it was made for us in some sense. One could argue that, it could come to that conclusion, right? We also knew that the stars, which we looked like they're fixed on a sphere, which don't move with respect to each other, go around us once a day, right? The moon takes around 29.5 days to go from new moon to new moon or full moon to full moon, right? And in fact, that defines a month. Month again is a big player in our daily life. And the planets, of course, do their own thing, but they're clearly also moving around us. And as we look at how the planets move as well in a little bit, right? And therefore, as people saw all this, people would wonder about this, and at some point it is natural for people to try and explain what they see. And science consists of not only coming up with an explanation, but also having an explanation good enough to predict what will happen in the future and try and match what's happening. Right? Your prediction does not match what you observe, then your theory or your model is clearly wrong. Right? And therefore, people started preparing mathematical models of how things move in the sky, how the planets move in the sky, how the sun moves or the moon moves, and so on. And these models, of course, assume that the Earth is the center of the universe, right? So that's called the geocentric model, or the Earth is at the center, and everything goes around us in some complicated orbit, right? And the first person to put together the mathematics, so the mathematics is being worked out in Greece a little bit here and there, in Babylon a little bit here and there. We're not really sure what happened in India at that time. The person who put together all of this into one coherent theory, a mathematical model, was Ptolemy in Greece, right? And it's called the Ptolemaic system. Of the geocentric model of the universe, where Geos, or the Earth, was at the center. Okay. And so in this model, the Earth is the center. Everything you see around us goes around us, and the faster objects are assumed to be nearer to us, right? So the moon is nearer, then Mercury, then Venus, then Sun, and then Mars, Jupiter, and Saturn, right? And the stars are far away, fixed on a sphere, which goes around us as a sphere. Now, and of course, they go at different speeds, and therefore they're different distances. This is the basic qualitative picture of the Ptolemaic model, or the geocentric model. And the mathematics, of course, was something he gave. Now, but even 2000 years ago, it was very clear. There's some extra chairs, or there's some chairs upstairs if you'd like to go up. Yeah, can go upstairs, please. But even 2000 years ago, even at the time of Ptolemy, it was very clear that the observations did not fit this very simple model where the Earth is the center, everything goes around us in nice circles. Well, assume it's a circle because it's the perfect object. And Aristotle at some point said, oh look, the circle is the perfect object, therefore everything has to go in a circle. And it's logical to assume that things go in a circle. However, even 2000 years ago, it was noticed very clearly that many things were not fitting this exact model mathematically. And one big thing is this retrograde motion. So if you look at planets in the night sky and track them over days and days and days, the planets go from west to east with respect to the background stars, and they take their own time to do so. But now and then, for a few months, they will start going backwards. Okay. Here I'm showing a simulation of the orbit of Mars in 2003, right? And for a few months, all planets will look like they're going backwards, east to west. And then after a few months, they're like, oh, I forgot, I have to go another way, and then they'll start going back in their normal orbit, right? And this happens, roughly every year-ish, and this is very weird. Now, if you assume all the planets go around the Earth in a circle, why would they suddenly go backwards and then come back, right? So this was obviously an issue. This retrograde motion in Indian astronomy is called Vakra, right? And the lots of beliefs about this, which is different, but in the astronomy part, Vakra basically is the planets appearing to go backwards in the sky for a few months before they go back in the same direction. Okay, so Ptolemy himself came up with the model where he said, okay, so the way to explain this idea is to explain observations and have predictive power, right? So he came up with the model. The chairs here, if you like. He said, look, empty point in space representing the planet goes around the Earth in a circle. The planet itself goes around that empty point in space, and therefore, as the planet goes around this and goes around the Earth, sometimes it will appear to go backwards. Okay, so I'll play it again. So the planet is on that small blue circle. The center of the small blue circle goes on a circle around the Earth. And of course, so now and then you can see it tries to go, it looks like it goes backwards. There's an apparent motion. It's a motion seen on the sky of it going backwards because it actually goes in a circle. That circle goes around us, and therefore now and then it will appear to go backwards. And therefore this smaller circle was called the epicycle. Okay. So every planet had a central point called the deferent, which went around us in a uniform circle. The planet itself will go in an epicycle around that deferent, which is an empty point in space, and therefore it will appear to go backward. Then you fit the epicycle size and the speed so that you can explain the observed retrograde motion whenever it happens, right? So each planet had to have an epicycle whose size and shape, etc., had to be fit so that it can predict the retrograde motion of that planet. Now, this was all fine, and in fact, this was also used in India, right? But as observations increased over centuries, in more observations happened. So you had observations for more number of years, right? And therefore, the model you had to explain data for many hundreds of years. And as more accuracy also happened in measurement, remember all of this is pre-telescopic, right? I'm talking about observations from 2000 years ago till telescopes were invented, right? So pre-telescopic observations, they had to add more and more epicycles because they found that the planet's actual position deviated from the prediction from that simple epicyclic model of Ptolemy, right? So then they had to add extra epicycle. Then they had to say, okay, maybe the center of the big circle is not at the Earth; it's slightly away from the Earth, because you found that the velocity of the planets was not same throughout its orbit. And therefore, just before Copernican revolution happened, the actual model of all the planet cycles is the thing shown on the right side. You can see it's fairly this is the one model used in Europe, right? So it's fairly complicated, right? And one assumes the assumption is that this is the one which led to the phrase wheels within wheels, as in things are overly complicated, right? And you have to keep, and they kept adding more and more epicycles to explain more and more accurate observations over time for each planet. Okay, but however, the basic premise was always upheld, which is that the Earth is the center of the universe. Everything goes around the Earth. So let's try and fix a complicated orbit of the planets around the Earth to match observations which are becoming more and more accurate and were being collected for longer and longer time as well, right? So if I have a theory which is based on observations made over 20 years, I can fit something. But if I had to explain observations over 200 years, then it might fail. I have to add more and more corrections, and then now we have 2,000 years of observations. So that's the idea. Okay. But it wasn't true. The basic premise was not questioned, was broadly accepted. The mathematical models were geocentric, but it's not completely true that nobody raised the question about it. The people who had raised questions about this from Ptolemaic time as well, right? So without Pythagoras himself and contemporary fellows who were Greek scientists at that time proposed a moving Earth. It wasn't a mathematical model. It was only a qualitative thing. Maybe the Earth also moves. How does it move? Where does it move? Why does it move? They did not say anything. They said maybe the Earth moves. And then the contemporaries like, oh, you're stupid. How can the Earth move? It's nonsense, right? So there were records by other Greek philosophers at that time who said, oh, Pythagoras is mad because he said the Earth is moving. Haha, look at it, right? Now, Aristarchus, who was probably one of the greatest Greek scientists who was relatively unknown, the 3rd century, and later Seleucus from the Persian Empire, proposed that all planets went around the sun. He actually said this, right? But there's no mathematics. He just said maybe they go around the sun, right? But then science depends on mathematical predictions to match with observation. So, but of course, it comes from theoretical understanding, conceptual breakthroughs, paradigm shifts, and so on. But then he just said this, and again, people said Aristarchus said this. So there's only one. So we don't have the Aristarchus' original reference. We have a reference of somebody criticizing this work, mentioning, saying, such a fool, he said that things go around the sun. Okay? And he also says the Earth rotates on its axis. Now, the two things, right? Copernican evolution is one, but then does the universe, does the sky go around us once a day, or do we rotate around ourselves? Is something which was actually proven in, at least in Europe, only in the 1700s by a person called Foucault. Okay? But in India, for example, Aryabhatta had said this too, right? 6th century CE, he said two things in his Aryabhatta. He said, one, that the Earth is the one which is rotating on its axis, and therefore it looks like the sky is going around us once a day, but it's not true. We are the ones rotating, just like Aristarchus and Seleucus said it before. And he also said that the Earth is hanging in mid-air, unsupported, which is also a very revolutionary thing to say. Imagine this: the Earth is not supported by anything; it's hanging in mid-air, and everything and everybody we know, all the people, everything are on all sides of the Earth, like the petals of the Kadamba flower. It's a very famous verse in Golapada. Okay, in Aryabhatta. So, but the first thing is also important. Not only does he explicitly say, one of the clearest examples in ancient times of the fact that the Earth rotates on its axis once a day, and therefore the sky looks as if it is rotating around us, right? He also, while explaining this, he also came up with one of the first explicit references to relative velocity or relative motion, right? He said the example he gives was, if you are on a boat in the river, you think you're stationary and the bank is moving, but actually the bank is stationary, you're moving. Same way, the Earth is rotating on its axis, and you think the sky is. This is, I think, a fantastic conceptual breakthrough in some sense. So he said this too. Okay, but we're still not touching geocentricity as such, right? But again, so this is again a video taken by my colleague Doje Amchuk, where he rotates the camera once in. So the camera rotated once in 24 hours, right? So this actual picture, if you wish, right? What Aryabhatta said is this, right? We are rotating once in 24 hours. The sky is stationary, right? And this can, I'm sorry if any of you have motion sickness, this might be very uncomfortable. That's why I said, no, decentering ourselves can be destabilizing, literally and maybe metaphorically. And so let the video play, because I think it's really cool. It's around a minute long. So what he did was he put his camera on a special mount. The mount is then programmed to automatically rotate once in 24 hours. Right? So the camera essentially tracks the sky. So the Earth seems to rotate, which is what is reality, right? So it's kind of an interesting. So I showed you a video earlier of the sky rotating, but this is what is actual reality, right? In some sense. So this is Aryabhatta video he made. So we're almost back to where we are. Is it kind of destabilizing a bit? Is it slightly weird to see this video? Or is it like, this is how it is? It's weird, right? So that's the point I want to make. Right. Okay. So Islamic astronomers, when I meant that, I mean the whole science school for a few centuries in near Baghdad, the House of Wisdom and so on. They also questioned the stationary Earth. Again, they didn't come up with a mathematical model, but they also said, why would the Earth be stationary when the sun is so bright, for example? Right? In India, in the Kerala school, how many of you heard of the Kerala School of Mathematics? You have. Anybody heard of the Kerala School of Mathematics? Yeah. Okay, so I think at some point we should have a talk on the history of science in India. I think it's important to learn the actual history of science in India. Right? What is that we actually did discover and place it in a global context, right? So Kerala School of Mathematics was between 1400s till late 1700s, right? And it was one of the, one would say at that time, one of the most prominent schools of mathematics and astronomy. In India, astronomy and mathematics went together, right? Everybody, Bhaskara, Aryabhatta, everybody was a mathematician and an astronomer. And therefore this gave rise to, for example, the Madhava series, which is like similar to the Ignis series, etc., came from the Kerala school, right? And Madhava's student is Neelakanta Somyaji, who then in 1501 gave this model where he said, look, he gave a mathematical model. He gave a mathematical model where he said, look, things are simpler if all the planets go around the sun, and the sun carrying the planets went around the Earth. Okay. So then Tycho Brahe then gave the same model, similar mathematical model of 8 years later. But Tycho Brahe gave it after Copernicus. He wasn't happy with Copernicus. He said Copernicus theory is rubbish, and he gave this model instead. So Neelakanta's work is in Tantra Sangraha. Okay. So there were already mathematics. So apart from qualitative objections, they now started having quantitative alternatives to this. Where they say, okay, everything goes on the sun. That makes the model easier. Sun, of course, has to go around us because that is something you don't want to touch. Okay, I think I'm going very slow. Maybe I'll speed up a bit. I'm very sorry. Okay, so then of course comes the Copernican revolution, right? And I'll tell you why we call it the Copernican revolution a bit later. So Copernicus then first proposes that, look, this doesn't make any sense at all, right? If we put sun at the center of the universe and make all the planets go around the sun, the mathematics becomes suddenly extremely simple. Right? And the fact that mathematics becomes extremely simple is huge evidence that it must be true. And he also said, look, sun is so bright, right? It emits so much light. It's clearly a very special object in the sky. And therefore, it makes sense that everything goes on the sun instead of going around us, right? So he gave the first mathematical model. Of course, at that time, the church at that time was very much against it. And then Galileo championed him, and then House Arrest of Galileo, all of that, Galileo play has been staged in Mysore a couple of times as well. I hope you all seen it. So he said two things. He says, one, the sun is the center of universe, and remember, universe at that time was what we saw in the sky, right? And all the planets, including the Earth, go around the sun. I mean, he does that. You realize that there's no epicycle anymore. Epicycles you can throw away completely. Okay, and exactly why that is so, I will answer if there are questions after the talk. But in this Copernican model on the left, where everything goes around the sun, as opposed to the geocentric model on the right, where everything goes on the Earth, you have to have these epicycles there. In the Copernican model, epicycles you can take and throw in the dustbin. Okay, and he said, look, this is a big reason. He said, look, these epicycles clearly are not needed anymore right? And why it is not needed, I'll explain later in the talk. And therefore, look, this seems like an obvious thing. This seems more like reality than the other one, because all these complications you had to keep adding wheels with the wheels all went away in some sense, right? So that is, but that is self. Of course, you might, I don't know how many of you read Sherlock Holmes, where Watson tells Sherlock Holmes, he just found out that the sun is the center of the universe, and he said, I hope I forget it because it's not useful to me, right? And I don't know how many of you are familiar with that, right? Because it was a huge thing, right? And so this is called the Copernican revolution later, of course. He didn't call it that. Why? Because he then said, because what he said is a mathematical model. He said, look, here's the mathematics, put the sun at the center of the universe, the thing becomes simpler, no epicycles, therefore this must be true. But there's a revolution in thinking, in concept, in paradigm. Why? Because he said the earth is not the center of the universe, right? This also meant that the earth moves like any other body. The earth, why should it move? It's like so special, right? Aristotle said the earth cannot move, right? And therefore earth moves like every other body. All of these statements, I would argue, are huge jumps in conception of our understanding of the world, right? The earth moves around some other body, right? Not only does it move, it moves around something else. So the thing it moves around must be more important than us, clearly, right? It does. Yeah. So I'll answer that. I have some at the end of the questions at the end. So if you put the sun at the center, the retrograde motion is explained very easily, and therefore you don't need epicycles anymore. That's the key. Okay. Right. And then the Earth is just like any other planet, because Mercury, Venus, Mars, Jupiter, Saturn go around the sun. We also go around the sun, so we just like Mercury, Venus, Earth, Mars, Jupiter, and Saturn. Okay. And therefore the sun is more important than the Earth. Right? Now different cultures might see this differently. Right. So this is why it's called the revolution, because it's a revolution of thinking, of a concept of the universe itself, right? And this is what I meant by saying decentering, right? So this is about decentering humans and therefore the earth. So what did it teach scientists of that time in some sense, right? Apart from the maths and the science of it, right? Earth is not special or unique, clearly, right? This is something which people did not like. Hence the whole house arrest by the Church of Galileo and all that, right? And we do not have a privileged position, right? So we're not privileged in any particular way. Earth is not unique, but so neither are we, therefore, right? And therefore, our point of view is not the central, most important point of view, right? And therefore, one could argue, following this, science as a whole learned many things from this Copernican principle, and therefore, we would see the universe same as anybody else would see from anywhere else in the universe, right? So, if you assume that the Earth is the center of the solar system, at that time, the solar system was a universe. So you're saying everything in the universe, the cosmos, whatever there is, the stars, whatever you think that they thought the stars were, had to go around us. All that is now gone, right? So in principle, how I see the universe is those different from what anybody else might see anywhere else in the universe. Right? These are all things which we learned later in some sense, right? And therefore, but there's a good thing to this too, right? It's a good thing to this, which means that I can use my observations to get a good understanding of the universe, because I'm not very special. Supposing you're very special. Let's say you cannot travel, you want to map out what is around you, right? So if you're living on the terrace of any one of the buildings in Mysore, anybody on the terrace of any building in Mysore can look around and get a good idea of Mysore. Supposing you're living in the palace, you're going to assume that all the roads are radiating away from me. You're going to assume that every building is smaller than yours. So you have a biased view of. So therefore, if you're not special, if you're not unique, then one could argue that our understanding of the universe through scientific experiments is a good enough representation of reality, because we're not really special. So it's kind of inverting the problem as it went. And therefore, this is a very strong statement, right? The laws of physics and maths we derive based sitting on Earth are also valid everywhere and at all times, right? So this is something we can talk about later if you want to, but this is a very strong statement to make as well. Okay, which I'm making, right? So there's a very famous cosmologist who said this some 40 years ago. It is evident that I got to show you a bit of many quotes in this talk. Evident that in the post-Copernican era of human history, no well-informed rational person can imagine that Earth occupies a unique position in the universe. This means this is no longer talking about whether sun or the Earth is the center of the universe as a whole, right? And therefore now, so that's the Copernican. So now I go to that's one part of my talk. The next part of my talk is now how astrophysics, since the invention of telescopes, has further decentered us, and in a way which is both good and bad. Okay, so there are two ways. I'm going to talk about only one way. The first way in which it's done it is that we are not the center of anything or special in any way. In many ways, much more than what Copernicus said. And we're going to run through some 15 also examples of that, right? So we're not at the center of anything or are special in manifold ways. And the second way in which we do this is enshrined in the mathematics of cosmology. If you look at Big Bang theory, it's something called the cosmological principle, which is a mathematical principle, which is embedded in the heart of cosmology, the maths of cosmology, which again says that we're not in a privileged position, which I will talk about again if there's time. Again. Okay, so I'm going to now talk about this part, right? So we're going to take Copernicus and then take it to an extreme, basically, using results from astronomy over the last 400 years or so. Okay, the first thing is that this is a to-scale picture of all the planets, right? The Jupiter, Saturn, Uranus, Neptune, Earth, Venus, Mars, and Mercury. So we see Earth is just a mid-sized rock. It's nothing special, right? The bigger planets than us, and we just among the 8 planets, we are just one of them, right? And this itself, I mean, I love this picture. This is not a real picture. They can real pictures and simulate it a little bit, but I love this picture because it gives us a really good idea of the scale of the planets and gives us a good idea of how big or small the Earth is, and therefore how important you think the Earth should be or not. Right? It's still very beautiful. Right? Anyway, now the last 10 years, so I'm going from the sun to outwards in scale. Okay, I'm going to go outwards in scale. The last 10 years or 12 years, we also discovered that almost every nearby star we look at seems to have planets around it. So for many thousands of years, we thought the planets are the ones around the sun, and people had hypothesized that other stars might have planets, but that is too difficult to see. But now we have good enough telescopes in space and on Earth, which have shown, now we discovered around 6,000 exoplanets. And every month there's a newspaper article saying, oh, there's an Earth-like planet that have been life, which is all hype. So don't believe it. But still, so we've been discovering planets around other stars wherever we look at least around nearby stars, right? And that means, again, Copernican principle says, if all the nearby stars you look at seem to have planets, then can I assume that all stars in the universe should also have planets, right? Because again, why is our name good special, right? So the observation of planets, discovery of planets around nearby stars, plus Copernican principle itself will tell you that other stars elsewhere should have planets too, right? So you see the power of the Copernican principle in some sense. If you assume that you're not unique or special, then any observation you make should be similar to how things are elsewhere. That gives you huge power. That's very powerful principle. Okay. Then the next fact I want to talk about. You all know the periodic table? All of you studied it in school? Okay, fine. So we know also there's a whole other talk waiting to be given, which is the whole Carl Sagan's we are made of star stuff, the fact that every atom of carbon, iron in your body comes from an explosion of a star, etc. That's a different talk, which we'll do, but that's not what I'm talking about here. What I'm talking about is the fact that the elements you're made of, forget where each element came from, each atom came from. The fact that we in our chemistry laboratory on Earth sit and find out all these elements, right? Carbon, nitrogen, oxygen, boron, fluorine, neon, sulfur, iron, copper, etc. are the same kind of elements in other planets, in other stars, in stars in other galaxies, all over the universe. This is a big thing, right? Which means, so I would argue this is also an extension of the Copernican principle by saying, look, we all made the same thing, right? In some sense, right? And if you could travel to a very distant galaxy and find a star where there are planets and this life, that life will also have carbon, nitrogen, oxygen, fluorine, neon, iron, copper, bismuth, lead, etc. It's not made of some weird stuff which we don't know about, right? So what we found in a lab is also what is there elsewhere. We are all made of the same thing, right? Nothing special about it. This understanding took around 300 years of astrophysics to find out, right? So, for example, the fact that the sun is the composition of the sun, the fact that most of the universe is made of hydrogen, etc., it was not easily discovered. It was a lot of painstaking research which got us there. Then, moving out a bit more, the sun we know is also a star. This again is an understanding we achieved after many centuries of research, right? Stars are very far away, they're very faint, they come out at night. The sun is a huge fiery thing which can burn things. The fact that they're the same thing is not apparent at all. To me, it's not apparent just by looking at it. But then, one can show that the sun is nothing but like other stars. Other stars are also as big and bright as our sun, and is one of many thousands you can see even the naked eye in the night sky in a dark site. So then, around 100, 120, 150 years ago, people started looking at nearby stars, studying the spectrum through a spectrometer, and then they found that our sun is an average star. What do I mean? It's average in mass, it's average in brightness, it's average in size, it's average in age. So our sun itself is nothing very special, though for us it's very bright and important. It is an average star. Even if you look at the stars, you can see with the naked eye in the sky, it's very average in all its properties. Okay. Now, then later we came to understanding that the Milky Way we see around us is the galaxy within which we live, and this galaxy has around 100 billion stars. Now, of the 100 billion stars, the sun is just one of them around which we are living, and we actually managed to figure this out. That's pretty cool, right? So the fact that we are only one of 100 billion stars in the galaxy itself was something again which took many years to figure out, and that again decentered us in a profound way. A physical decentering also happened because when we mapped our own Milky Way galaxy, this is a depiction of our Milky Way. We found that we are not even in the center of our own galaxy, right? We are in the galactic suburbs somewhere, 2/3 of the way out in the spiral arm, right? So our sun is not even occupying any special portion of our galaxy. It's like far away in the suburbs, right? So it's not even an empty road of Milky Way, right? And then Hubble came around in around 1920. So the two people on top are Curtis and Shapley. There was a huge debate called the Curtis-Shapley debate. You can read about it later. At that time, people thought, around early 1900s, people thought that our Milky Way galaxy is the universe. Okay? Because people knew the size of our distance to nearby stars, and all you could see was the Milky Way, and all you could see were the stars. And our universe, our conception of the size and the scale and the grandness of our universe is limited to our galaxy alone, just as hundreds of years ago, our concept of the universe is limited to our solar system, right? So then the solar system, we went up to the Milky Way galaxy, but we thought that was the universe, and then at the end of the Milky Way galaxy, there was nothing much, there was a space, and what happened much beyond to something people were not really could not figure out at that time. But there were these small gaseous, they call nebulae, gas clouds you can see with the telescope, right? Some of them were clearly forming stars, like the Orion Nebula, which you might have heard of. But some were looked like they were kind of distinct by themselves, okay? These gas clouds, okay? And these gas clouds, there was a huge arranged debate, public debate between Shapley and Curtis, where Shapley argued that these gas clouds are within our Milky Way. That was the end of it. Curtis argued that these gas clouds are actually their own galaxies, just like our Milky Way, and they're very far away. And then the idea was, this is ridiculous. I mean, how can you have that means you're expanding the size of the universe by many thousands folds, right? So these gas clouds are small gas clouds in our Milky Way, as opposed to they're again their own Milky Ways. And this debate was ultimately sorted out by Hubble. Hubble did two great things, right? We all know Hubble for one thing. What is it? Hubble. The person, not the telescope. That's what named after the person. But we know Hubble, Edwin Hubble, for having made one big discovery, which was the universe expanding, right? But he made an equally big, I would argue, even more important discovery before that, which is that he was the one who proved that these small gas clouds, like the Andromeda Nebula, were actually galaxies in their own right, and therefore, at a stroke, he made the universe around thousands of times bigger than we thought it was, right? So, if they were galaxies as big as ours, and you saw so many of them through a telescope, and there's so many of them, then you could suddenly imagine that your imaginary universe expanded by thousands of folds suddenly, right? So he did that. And the Andromeda Nebula was then renamed the Andromeda Galaxy, right? The Triangular Nebula was renamed the Triangulum Galaxy, and so on. So that's something Hubble did. Okay, so now the universe has now become much bigger. Now the Milky Way itself is not special anymore. Now we're saying the other galaxies, like the Milky Way, which are as big or bigger or smaller, etc. So now we've gone from the sun not being in the center of a galaxy to there being other galaxies too, right? So now where are we in this picture, right? One has to then look. Okay, now these are all pictures taken by the Hubble Space Telescope. So our Milky Way galaxy itself is not very special. It's a medium-sized spiral galaxy. These are actual photographs of other spiral galaxies, and our Milky Way probably looks a bit like somewhere in between two suns, something like this. Okay, it looks much better on my screen. It looks very pretty here. And therefore, the Milky Way is just one among billions and billions of such galaxies. There are galaxies which are much bigger than the Milky Way, 100 times bigger than the Milky Way. The galaxies which are 100 times smaller than the Milky Way. Right? So again, we are seen to be fairly average, just like the sun was an average star. Okay, so now we expand. Now we've gone up to other galaxies. So let's go even further, right? So the Andromeda galaxy, Milky Way galaxy, and the Triangulum galaxy, that is this, and this, form something called a local group of galaxies. They are bound together by gravity, along with a number of dwarf galaxies, like all these mosquito type things you're seeing, and therefore this is called a local group of galaxies. We are one of the three big bullies in the galaxy, gravitational bullies, if you wish, and the others are all along with many dwarf galaxies going around us. The local group of galaxies itself is one among is part of the Virgo cluster of galaxies, which is made of many such groups like our local group, right? The Virgo cluster is somewhere here, and the other clusters like the Virgo cluster as well, right? And many clusters of galaxies together form a supercluster called the Laniakea, which is all over. This is all mapped out. These are all actual maps, right? So all of these I'm showing you are actual maps which we made by locating galaxies, measuring the distances, putting them in the correct location in 3D space, right? So now, and the observable universe itself, if you go even beyond this, now we know has observable universe is the universe which we can potentially see through a telescope if it was big enough, okay? And that has around 1 trillion galaxies. A trillion is 1,000 billion. And each galaxy has around 1 billion galaxies, stars, and therefore now the observable universe we know has 1 million billion stars. Right? Okay, so this is a small. It's called the Hubble deep field, and this each thing you see here is a galaxy of its own, and they are very distant galaxies. Okay, so now where are we? We have now come from the Earth being in the center of our geocentric universe to us being in the corner of a galaxy like other stars, and there being trillion galaxies with a total of million billion stars, of which a good fraction will have their own planets, right? And what happens in those planets is, of course, anybody's guess, right? So we've come a long way, haven't we? Right? So in some sense, the decentering has been of epic proportions in some sense, right? But has it been? Is it always a bad thing to decenter? Of course, our egos are hurt, but big deal, right? It's not, and this gives us a different perspective of the universe, and I will come to that in a bit as well. So, quote Carl Sagan, who always says things best. Who are we? We find that we live on an insignificant planet of a humdrum star, humdrum as in like a normal star, lost in a galaxy tucked away in some forgotten corner of a universe in which there are far more galaxies than people. Okay. Now, so this is a hit on the head of anybody who thinks they're very special. But I also want to pause a bit and talk about the fact that sitting in an insignificant planet of a humdrum star lost in a galaxy tucked away in a forgotten corner of a universe, we've been able to discover all this. Isn't that cool? Right? So that's the other side of the coin, right? So we have been discovering we are not special, blah 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 blah. I ran through the entire gamut of things, but we also been able to, sitting on this insignificant planet, figure out all of this. And that does it make us special again? Does it make us special again? Is the question I want to pose to you, right? In some sense, it does, doesn't it? Right? Of course, one could argue that the life in other planets also figured it out. Therefore, we are just like that. But for us, this is something special. It's a moment to kind of take in, and I think I feel a bit nice about ourselves. Even though I've been spending the entire half an hour telling you you're not special, you're nothing. Okay, so. So this is basically about physical decentering, right? There is a physical decentering of gigantic proportions, right? Now I'm going to take two more steps and talk of a more a decentering of a different kind, right? Not only we're not center of anything, we are one of many, etc. We're not even the things we know of are not even what the universe is actually made of. Okay, and that is a decentering of a different nature. The first part, of course, is called dark matter. Do you know dark matter? How many of you heard of the term dark matter? Do you know what it is, roughly? You know what it is?
That's the thing we don't know.
Exactly. It's the thing we don't know. We just say dark. The scientists are very clever in that. Okay. So the matter we are made of, I said, everything is made of hydrogen, helium, carbon, nitrogen, oxygen, iron, etc. It's a lie. I was lying to you, right? All matter which is visible or interacts with light, and therefore we can actually observe directly or indirectly through our telescopes, is made of protons, electrons, neutrons, either individually or locked up in atoms or locked up in molecules. But we also know now very clearly that only constitutes 15% of the total matter in the universe. the remaining 85% of matter, we know is matter because we can see its gravitational effect on the matter we know, right? But we don't know what it is made of. We know it is not made of what we know of. Okay, so we know 85% of the matter is defined as that which exerts gravitational force, right? So if you look at the whatever is the universe exerts a gravitational field, 85% of that is not made of electrons, protons, neutrons, quarks, gluons, photons, neutrinos, everything you know. It's something else. We still do not know what. It's one of the big open questions in astronomy research. But only 15% of it is made of those particles we know. So we're not even made of the majority of matter in the universe. Now, the one more thing, and this is the final nail in the coffin, right? Is that this atoms we know, the neutrons, protons, electrons, made of 5% total energy. This is the 15% and 85% I told you. This makes total matter which exerts gravity. But around 68% of the energy of the universe is something called dark energy. Again, you heard dark energy, that we don't know, right? If this dark energy we know exists because we can see that the universe is accelerating. The universe is expanding, like Hubble discovered, but the expansion is accelerating. And that acceleration, because we see the acceleration, we can infer there's something called dark energy. We can infer some of its properties, we do not know what it is, right? So, if you look at the total energy budget of the universe, we are only made of 5%, not even 15%. Now, this, potentially is embarrassing. Any other field, the experts tell you that, we are great, give us money to build more instruments, but we only know 5% of what is on that, we fired immediately. But astronomers, somehow we keep getting our jobs because, even though we agree that we do not know 95% of what we study. It's kind of very embarrassing in a way. That's also what makes it exciting, right? So it's exciting because this is the forefront of research in astronomy around the world, right? People around the world, including India, are trying to figure out what is the dark matter, what is the dark energy, right? So it's exciting that is an open question, but one could argue it's also kind of epistemologically embarrassing. Okay, so let's go to Stephen Hawking. What did he make of all of this? So he said, we now realize that Copernicus' result is but one of a series of nested demotions. That's what I meant by saying successive dethronements, right? Nested demotions, overthrowing long-held assumptions regarding humanity's special status. We're not located in the center of the solar system. We're not located in the center of the galaxy. We're not located in the center of the universe. We saw that already. We're not even made of the dark ingredients constituting the vast majority of the universe's mass. So this is like the final layer of the coffin, right? So we really don't matter. Okay, pun intended. Right. So what is the cause? So let's go back to the Copernican principle. The Copernican theory was to put the sun at the center of the solar system. The Copernican revolution is what it implied in terms of man's place or human's place in the universe. The Copernican principle says, therefore, what you learn from it is that we do not have a unique or special position in the universe, and therefore, if your data shows that you're somehow unique, the astronomers will immediately say your interpretation is wrong. If your data leads you to say that you have a unique position, some way, and this is not just true of solar system, it's true even now. When I give you an example, good example from few decades ago, then astronomers immediately jump to the conclusion that I have made a mistake in my analysis, which makes me to infer this, right? That's the Copernican principle. And hence, if you find that your theory leads you to such a conclusion, then you better re-examine your assumptions. So let's go to Feynman. What did he say? The first principle is that you must not fool yourself, and you're the easiest person to fool, right? That what he meant by that is that we do not take into account our own assumptions and biases. Therefore, if we find something which conforms to our biases, we do not dig deeper, right? And scientists are trained to do that, to dig deeper, to not, and to not go by, if you get a result which conforms to what you've been hoping for. If you're a good scientist, you're trained to not take it at face value, but to question it, because if you don't, somebody else is going to, right? So therefore, and one is also argued that the Copernican principle can also be seen as a statistical principle. What do I mean by that? I mean that statistically speaking, we're not special. We could be, for example, our galaxy could have been one of the largest galaxies in the universe. It could have been, right? There are some galaxies which are very, very big. We could have been in the galaxy, right? And then if you find that your galaxy is one of the largest, you have to just accept it. We might have lived. There's a lot of stars which are much bigger than our star, the sun, right? We could have been a planet around such a star. We could have been, right? The largest star in the solar system, in the galaxy, will have planets around it with life on it probably. The biggest galaxy or the smallest galaxy or the weirdest galaxy or the weirdest star will also have life on it. If you're there, then you might end up figuring this out. But statistically speaking, on the average, you would probably not find yourself special as the Copernican principle. So the statistical principle in some sense, right? And therefore, people have been saying, okay, this is a principle which is a guide. It's not a law or a science. It's not a science theorem. It's a guiding principle. And a statistical principle is a guiding principle to examine things around you and come to conclusions, right? And therefore, one is also applied. For example, now of course we know there are planets around the stars, right? But before we discovered the 6,000 planets, people were saying, look, why should our sun be the only star with planets? Our sun is only an average star. There are so many stars like our sun. Therefore, even if we haven't discovered planets around the stars, the Copernican principle will tell you that they probably do exist. So better go look for it. Right? So in that sense, a statistical statement, right? So does life exist? This is a big question, right? This is one of the biggest questions science has to answer, right? So does life exist elsewhere, and how probable is it? Now again, if you could have a million, billion stars in the galaxy, in the universe, and at least there's one planet for every star, a billion, whatever you want to, planets in the universe, then again, probabilistically, how probabilistic we're only ones with life? Right? The other hard question to answer, is there life? Is there evidence for it? How did it occur? How did it form? Evolution? Did the X-ray of the sun, of his parents, stars, see it, etc. But just as a guiding principle, a probabilistic statement, if we're finding that almost all stars are planets, then it's a bit silly to assume that we are the only ones with life, right? Darwinian evolution shows that humans are not just even on Earth. No, we don't assume that we are the most intelligent creatures and so on and so forth. Of course, we're the only ones who build cities and also bomb them. If you look at all the animals on Earth, but it is an accident that we came up, right? In some sense, the fact that we became intelligent and formed societies was an accident of evolution, right? The dolphin could have done it instead, or a dog could have done it instead. This accident of evolution, we were the ones who doing it, right? So even in evolution, even in Darwinian evolution, tells you that though you might be the intelligent species, that is just an accident or probabilistic accident, right? Would life elsewhere be based on carbon, like we know, or could be based on silicon? Could be with water, without water? One doesn't know, but probabilistically speaking, it's very silly to assume that it will all be like us, right? And the laws of physics are the same across the universe. This we think is true, right? And that again goes back to the earlier point I mentioned. Okay, so again, another famous astronomer, Neil deGrasse Tyson, to declare that the Earth is the only planet in the universe with life would be inexcusably big-headed of us, right? So this is what we're talking about. Okay, so I'm almost at the end. So to get a branch out of science into other domains, which probably shouldn't, if Copernican principle has taught us that if you think you're unique, you probably aren't, then is it also true of personal? I would just ask you, right? Is it true of personal experience, right? If you think that your community, however you define it, is special, then all of what I've taught you, all of what I told you, should teach us that that's also something which is probably not true, right? One would argue that, right? And I put a man in the picture because usually it's a man, not a woman, putting in the center of the universe, right? So think of other categories, just like planets and stars and galaxies. Think of ethnicity, nationality, religion, caste, class, race, physical ability, disability, sexual orientation, gender identity, species, right? If you think that your particular identity group is somehow more central or special, is that a problem? I'm not asking is it right or wrong. That is a different question for humanities to answer. I'm not talking about the morality or the ethics of it. I'm asking you, is it even a probabilistically correct statement? That's the only thing I'm asking you from a science point of view, right? Of course, there's ethics and morals to it, which is not something I'm getting into. But is it even a probabilistic statement? If you're born in a particular sub-community of any of these, what's the probability that you're born in that particular combination of communities, which is the most special on Earth? One has to ask, right? So the Copernican principle hopefully will tell you that's not true either, right? So I would argue Copernican principle also tells you, addresses this point of, it's a more sociological statement, but I would argue one could also, talk about it. Okay, so there's also something called the anthropic principle, which is again the counterpoint to everything I'm saying, but in a very interesting way. And I'll end the slide after that. Is that so? For example, we have the fundamental constants of the universe. We have velocity of light, we have the gravitational constant, we have the Planck's constant, we have Boltzmann constant. All these are constants in our entire universe, right? If they're very different, right? Let's say the Planck's constant was like 100 times more, or the speed of light was, some 100 times, 1000 times less, and or gravitational constant was 10 times stronger or 10 times weaker, then life as we know it could not have occurred. There could be other forms of life, but life as we know it, even the stars as we know it, would not, a universe would not be the same as it is. It would be a different universe, right? The universe as it is structured by the values of the fundamental constants of the universe, which are the physics constants, right? So, so the anthropic principle says, so the question is, why is it? Why is the C equal to 3 × 10⁻⁸ meter per second? Why is Planck's constant 7 × 10⁻�34? Why is the gravitational constant 7 × 10⁻11? The answer is very different. You will not be here to ask the question. Is the anthropic principle. So, kind of a counterpoint to the Copernican principle. But this is a very valid point of view. And I want to combine these two and end here. So, what does astronomy teach us? Right? We're not special. That I've seen, and I hammered it home, I think, very well over the last 1 hour. This can be humbling, but also allowed us to understand the grandeur of the universe just a few centuries. Right? The fact that we know all of what I presented to you, right, sitting here on Earth, is again something we can look on with awe. Maybe not. You might want to be proud of it, but I would say look on with some awe, right, rather than being proud, right? But our existence also presupposes things to the universe much different. You not be here to observe it, and both are statements of probability. What is most probable is the question, right? And therefore, I would say Copernican principle helped us question our assumptions and be skeptical of any parochial or partisan claims in science, and one could also argue in other branches outside science too. And therefore, it should help us with some level. I think it gives us a different perspective of who we are, our place in the universe, our perspective of where we are. And of course, given after all I said, ultimately we are sitting on Earth, and for us, of course, it is very special, right? And therefore, we should take care of it, I think, a bit better than we are right now. So, of course, Render comes. Second, every one of us, after having said everything, I think Render came with him, which says, he said, every one of us is in a cosmic perspective precious. If a human disagrees with you, let him live. In 100 billion galaxies, you will not find another. Though, there are many billions of galaxies, stars, planets, life. Each of us is still, in some sense, personality-wise, very unique. And he also said we are a way for the cosmos to know itself. This is a more of a philosophical point. So I'll stop there. Thank you. I think in 1 hour, sorry about that. But
Yeah, 1 minute extra.
But suppose 3 photon star just get released in a star in a distant galaxy. One of the photon they pass through different layers, like they pass through different black holes near the black hole. They bend into different angles, and somehow those 3 photons land on Earth. Because it is said that the photon doesn't experience time. Right?
does experience?
Photon doesn't experience time.
Yes, okay.
Time stops.
Okay.
Now the one of the photon somehow reaches earthly and falls into the eye of, say, Jesus Christ. So another photon comes and falls into the eye of Gautama Buddha. The third photon, after passing through different,
This is a good science fiction story in the making, but yeah, please go ahead. Yeah.
it goes and falls into the eye. I am standing outside this Kurumpanagar and it falls to my eye. So there is a time gap. Now you are telling that the time should not be felt by Einstein. According to Einstein, time is not felt by a photon. But again, there is time dilation. Difference is there. So how do you explain this?
No, you don't have to go to such an extreme example, right? I mean, if I shine a torch, it will illuminate you, and then the light will illuminate you, then will illuminate you. So it does, of course, for us, the light does take time to travel, right? If I say something is, if I emit a signal from a Voyager spacecraft, it takes a day to reach us. Right? It doesn't take anything, right? But then in the photon's frame of reference, there's no time difference, right? And these are counterintuitive things. You have to look at the mathematics to see why it is so. All I can say at this time, at this context, is that maybe it goes back to what I was saying in the talk, right? So quantum mechanics and relativity are counterintuitive, right? Because our intuition is based on the world around us. So I'm not going to answer your question directly. I just want to say something and stop there. Our intuition is not like comes from somewhere from our teeth. Our intuition is built by what you see. The small child drops a stone, sees it falls, it knows that things fall on the ground, and so on, right? So intuition is built by things around us, and things around us which we experience with our senses is limited by our bodies. Therefore, it's limited to small velocities, small distances, small masses, and so on. Right? So I just missed the point, right? And And it's only when we realize that is not the entire world, right? And scientists started measuring things more and more accurately with instruments. You realize that if you go very, very fast, your intuition breaks down. You have to apply special relativity. Or if you go near very, very massive objects, our intuition gain, which was codified as Newton's law of gravity, is no longer valid. You have to apply Einstein's theory of gravity. Or the fact that if you go to very, very small distances, our intuition codified as classical mechanics is not applicable. You have to do quantum mechanics, right? And therefore, what you necessarily find in quantum mechanics or relativity will be counterintuitive. But the mathematics of it is consistent because we tested it again and again and again and again. Now, that's all I can say at this moment. Anything more than that is a separate thing by itself. So I won't get into that. Is that all right? Yeah.
What is the
Sorry, you want to add something to that point first?
I was just thinking, not necessarily that it is actually based on only that physical reality. Because there's a metaphysical energy which is unseen, which also basically caters to.
I cannot answer to that because there's no scientific evidence for any such thing. So I cannot as a scientist answer to that. All I can say is that nobody is yet demonstrated any evidence for anything like that, right? That's all I can say.
Sir, what is that question?
No, sir. Order hopefully first to that question.
Thanks for that. So what does astronomers say about UFOs and extraterrestrials?
Yeah, so UFO sightings, right, have all been proven not to be true, which was being investigated, right? Again, well, it doesn't mean that it cannot exist in principle, right? And in fact, we'll all be very, very thrilled if somebody visited us, maybe, I don't know, right? So people are searching seriously for both signs of life elsewhere, as well as maybe there's a visitation or signals being sent to us. But so far, every instance which has been investigated has been shown to not be true. Okay, and if you look at the statistics, if you look at all the UFO sightings, they're all in the US. Why would it seems silly that you come all the way only you may go to other places. In the US, it's only been seen in one belt. This is near Roswell, right? So there are a lot of conspiracy theories that the US military has some aliens locked away and all that. But then there are conspiracy theories. Science can only address evidence which is placed before them, right? So those UFO sightings, in fact, there have been studies which looked at UFO sightings of people, and in the studies which have been done, something like 95% of them ended up being Venus. This happens because we don't know the night sky well enough, right? So you go once and see Venus suddenly, and you're like, oh my God, this is so weird. Instead of seeing a night sky every day. So most of the sightings of UFOs have ended up being Venus. Sometimes in the moon, right? So once it's been studied, which people looked at and say, okay, I will take your claim at face value and investigate it, try and find out. In every case, it's been proven not to be so, right? So unless there's evidence, unless somebody comes and somebody may walk in now and then we'll see, right? But unless there's evidence, there's nothing we can say. And what was being investigated has been shown to be, I would say they're lying. I would say that it's very easy. Humans are excellent at pattern recognition, right? So they've all been mistaken. Venus has been mistaken. If you move in a car, you look like Venus is moving along with you, so you think the spacecraft is following you, or the moon looks a bit weird when it's rising or setting, right? So we mistake certain phenomenon for UFOs. That's been the conclusion of every investigated example. That's all I can say. Yeah. You want to add to that?
Hello, sir. With your Copernicus principle, could it also be that it can eradicate racism community?
I'll repeat it. Yeah. Sorry.
With the Copernicus principle, it could also eradicate racism, communism, and all the small isms that we had.
Well, that was my. I sneaked in a slide here, right? People. I think there are far better reasons to not be prejudiced against people than Copernicus. There are far more reasons coming from morals and ethics than this. But I'm arguing that Copernicus will add to that list of reasons to not discriminate against people or think that you're better than them. That is my point. Right? Sorry, yeah.
ಇಲ್ಲಿವರೆಗೆ ಅನ್ವೇಷಣೆಯ ಪ್ರಕಾರ ಭೂಮಿಯ ಮೇಲಿರುವಂತಹ ಜೀವಿಗಳ ತರ ಬೇರೆ ಯಾವುದಾದ್ರೂ ಗ್ಯಾಲಕ್ಸಿಲಿ ಕಂಡು ಬಂದಿದೆಯಾ ಇಲ್ಲಿನ ಅನ್ವೇಷಣೆ?
Have you found any life form like?
Okay. So let me kind of give you a slightly longer thing because many of you have questions about UFOs usually end up being true. So One is, of course, the fanciful, oh, I saw something, and then people are like, oh, I was abducted and come back. I'm not going into those things at all, right? I'm talking of actual science. What can actual science tell you, right? So the two ways in which astronomy tries to look for life elsewhere. Okay, one is a lot more extensive, which is that you don't assume that all life is intelligent and can communicate, right? Even in our Earth, if you look at life has existed for around 2.5 billion years. So only for 70 years we've been able to communicate into outer space, right? So assumption is that if you assume that that's not true, and therefore you want to look for life as defined as even by microbes or plants or bacteria, right? So how would you search for that life? Because that's going to exist for longer time than intelligent life probably, and therefore you probably end up discovering it easier, right? So the James Webb Space Telescope, how many of you heard of it? It was launched recently, right? So one of the things it does is to do this, which is that so you look at the stars, nearby stars around which we know there are planets, and the planet is passing exactly between us and its star as it goes on. So the star is here, the planet can go around this way, any angle, but if it's going exactly this way, it will then cross the star as seen from Earth. Of course, you can't image the star, right? So the way these planets are discovered is that you look at nearby stars very, very accurately all the time, and then you suddenly see that its brightness dips by 0.01%. 0.01%, or even less than that sometimes, right? For a few hours. It goes back again. You think your instrument is malfunctioned, fair enough. Then after 40 days it repeats. After 40 days it repeats. Then you think, aha, then I discovered evidence for a planet going in front of its star and absorbing 0.01%, blocking 0.01% of its light, for example. Right? That's what happens. So, for example, during a total solar eclipse, what fraction of a sun's light is blocked? 100%. Right? But you know there's something called Mercury and Venus transits. How many of you heard of Mercury transit and Venus transit? Right? So Mercury and Venus move in front of the sun as seen by Earth, and then it also blocks like some 0.01% of the sun's light if you add the entire light of the sun. Of course, you can image the sun so you can see it moving, which is fantastic, right? 2013 Mercury transit happened, 2013 Venus transit happened, 2019 Mercury transit happened, right? So you look at a star's light and you measure the star's light very accurately, and then you see these dips or very, very small dips, and then you can infer there's a planet going in front of it, orbiting it. And by studying multiple orbits, you can measure the planet's radius, distance from the planet, from the star and its mass, and so on. Now, what JWST is doing, and there was a few months ago, there was a newspaper article saying they discovered life, which then later turned out to be not true, is that when the planet goes in front of its star for those few hours, the planet's atmosphere will change the light of the star passing through it. Remember, the planet itself is blocking 0.01% of the star light, right? And then 0.01% of that 0.01% will be affected by the thin atmosphere of the planet. You look at the spectrum of the planet at that time and try and see if there's evidence for chemicals in the atmosphere which could come from life. This is a extremely difficult thing to do. That's one of the main things the James Webb Telescope is doing, right? And there was a false alarm a few months ago which said that around this Kepler 31b or something, they did discover methyl sulfide and dimethyl sulfide, which is on Earth is created by microbes mainly. Then it turned out that the detection was not really true because it was a very, very small dip. That small dip went away when they analyzed the problem, right? But that's one way of detecting biosignature chemicals. This is what is called biosignature chemical in the atmosphere of the planet while it transits its particular star as seen from us. It's a very, very difficult experiment. That's one way to do it. The other way to do it is to look for signals from intelligent life, right? And that's also something we've been doing. The SETI, Search for Extraterrestrial Intelligence. How many of you seen the movie Contact? Older generation, Jodie Foster and all that, right? Okay, so movie Contact is about that. There's also a book by Carl Sagan made into a movie where we are emitting signals. So we have emitted certain signals towards certain directions where there are lots of stars, they call globular clusters, hoping that some of these stars might have planets which will detect our emission maybe like thousands of years later and so on. But then apart from emitting these certain signals, we also emit a lot of junk, right? So every SARS Bahu serial you have, every news channel you have is emitted to interstellar space, which should be really embarrassed, right? So 70 years ago when TV and radio started, the radio waves leave our atmosphere and expand to the speed of light, and they have reached 70 light years by now, right? So all the planets within 70 light years have received our TV and radio signals, and if we decode it, we're going to be very, very embarrassed, right? Now, but then that is something we're doing accidentally, right? But we also could emit things in a particular direction on purpose, right? Which we have done. So the other thing is in the radio, and in the radio, because radio can travel through the galaxy without being absorbed by the gas and dust easily, we're looking for these signals emitted by potential intelligent life, right? And that's the second way in which we are trying to detect life. Neither of them have given anything yet, but it's a very serious attempt being done by very serious astronomers, though it looks like science fiction. It's a long answer, but I want to do this because the question which keeps getting asked by people.
Short answer is we have not found.
Short answer, sorry, I should write with that. We've not found anything so far. Correct. Yeah. Yeah, please.
Maybe we can add another layer of involvement, but this is just a possible theory, the famous theories about multiverse.
Yeah,
And
so
then,
possible.
the dark matter and dark energy sometime in that kind of theory would be accommodated as the effect of other universes.
Yeah, so there's a speculative theory that there are other universes too. So then, of course, there's one more level of dethronement. But the speculation at the moment, there is no evidence for it, neither is going to come anytime soon. But if it is true, there's some it's speculation because there are some theoretical arguments for it, but that's all in the realm of speculation, right? So if there are other universes as well, then of course you're right. There is even more, one level of extra decentering in some sense, of course. Yeah, but I think we've gone enough. I mean, I think we have destroyed any notion of specialness by now, as it is hopefully in the last 1 hour. But yeah. Other questions?
That has specialness behind you.
Sorry.
The aspect of
Yeah, that's why I said I want to come back to it in the sense that though we are not special in the way I described, in some sense, each of us, one could argue that's what science is. But each of us are also equally precious, like Carl Sagan says, right? And therefore, we're not special doesn't mean we just treat each other badly because of that, right? The idea is that we are special. We have been able to do so much together. We have been able to discover all of the science. I already talked about astronomy. There are other sciences too, right? Chemistry, biology, and so on and so forth. We also build societies. We have done terrible things. We've also done great things as when we come together as culture, as a civilization, right? And of course, and while understanding that we shouldn't center ourselves, not centering ourselves doesn't mean we're not unique, right? So individual uniqueness or individuality doesn't contradict decenter, right? So I'm okay as a citizen of India. It's not I'll be happy only if I'm like the most important citizen of India, right? I can have a fulfilled life as a citizen of India while knowing I have the same rights as all 1.4 billion people. So the difference between, but then my experience are unique to me and they're special to me, the people, my friends and family are unique to me, and so on, right? So sometimes uniqueness, your individual uniqueness doesn't have to contradict you not being at the center of everything. You don't have to be a center, right? And we know people in our lives who are happy only when they're center of attention. We know people who are happy when they're not center of attention, right? So I'm arguing that one could apply this to a lot of other sociological situations too. Yeah. That's Does that make sense? Right?
Einstein and Niels Bohr were roaming around the city and it's told that uncertainty is there. So in quantum mechanics, uncertainty is there. So Einstein asked Niels Bohr, I'm seeing this moon. If you don't see this moon, you need to say that it doesn't exist, is it? He said. But now that we have got recently that at the atomic level, we are telling that according to quantum mechanics, everything is uncertain. The double slit experiment recently did again with the atomic level precision. So that means to say that nothing in the nature is real for us.
Okay, so let me. Do other people also relate to the question? Does it make sense to people? Okay. Again, going back to the fact that our intuition is based on reality, a lot of the statements of quantum mechanics or relativity, when communicated in the public domain, have been miscommunicated, right? So uncertainty principle doesn't say everything is uncertain. I don't know where I live. I don't know where anything. That's not what uncertainty principle is. The uncertainty principle is a very mathematical statement. Okay. So purposely I'll get my talk very qualitative because I want to talk of the implications of scientific discovery. But science is, at least physics is all about quantitative stuff. If you cannot measure things and describe the equations, it's not physics, right? So The uncertainty principle is a very specific mathematical calculable statement about uncertainty of certain quantities, and how uncertain they can be is also described by the same equation. They cannot be completely uncertain, right? They can't do anything they want to. That's not true, right? So the uncertainty principle in quantum mechanics is the uncertainty, level of uncertainty in quantum mechanics is prescribed by the uncertainty principle of Heisenberg, right? So it is not, so you cannot, so that doesn't mean that I don't know whether the road will be outside when I go, for example, right? That is not what it means. No, that's not what, that is not what quantum mechanics is. No, that's not. No. Let me finish. That is not what it says in my point, right? So, quantum mechanics will tell you these statements of uncertainty, observability, etc. They are very strictly defined. Anything in this is very strictly defined, right? And they are applicable to very, very small scales when observed or when experimented upon in very particular ways. Okay, it does not apply to macroscopic things around us. Okay, the largest macroscopic thing you could observe a quantum mechanical phenomenon was this very, very small device for which they got the Nobel Prize in Physics last week. Okay, and they got Nobel Prize because it was actually not seen, but measurable in a macroscopic small device. That is the extent of it, right? So the larger question of if I don't see it, is it there? It's not quantum mechanics. That's an epistemological question, right? So that's something philosophies are talked about, right? No, as far as I understand, that's not true. What I'm saying. Maybe you can send me reference. I can take a look at it. But the argument about quantum mechanics is among the physicists has not been about macroscopic objects at all, right? It's only about microscopic objects, very small scale objects in particular experimental settings, and the level of uncertainty or the Schrödinger's cat paradox, etc. are not to be taken outside the particular context in which it is said, right? If you apply it to things around us, you will end up like you're saying with some fairly counterintuitive things, right? So it's a moon. So uncertainty principle doesn't say the moon can be the moon is not. That's not what it says, right? It talks specifically about things at very, very small scales when looked at a particular way, right? The rest of it, of course, you have to look at the theory, look at the maths of it, right? So Bohr and Einstein's argument wasn't about that. Their argument was again about laws in the microscopic domain, whether probabilistic laws are at all real or not. So that's a different issue, right? And that's been settled in various ways since then. It's not about the macroscope. If I observe it, if I don't see the chair, if it's not there, if I don't see the moon, it's not there. That is a more of a philosophical question, which even Indian philosophy systems, that question has been asked many times. Right? So if you look at various, so 3 or 4 of the philosophy systems of India, ancient India, this how do you know what is true? How do you know what knowledge? This has been asked in many philosophies. In the scientific domain, in the context of physics, they have very particular meanings. So uncertainty principle has a very particular meaning. The fact that, for example, time is different if you move at different velocities it's not the same as saying if I'm sitting in a very boring talk, like probably this is time moves very slowly. That's not what relativity is. So though popular media would say that, right? If you sit in a very boring movie, time moves very slowly. That is not the same as time dilation talked by Einstein, right? So these are all very specific, quantifiable things in very specific settings which can be measured in the laboratory, right? Those principles, if you apply to the world around us, we will be led to seemingly nonsensical statements because that's not the domain of applicability of those theories. That's all I can say at that point. Does it make sense? Does it address your point a little bit?
Actually, what happens is that open-ended interpretation of
I get shocks from this one. Okay.
open-ended, what you are inputting is open-ended interpretation. Bohr had a student whose name was Henry David, if you know that. They had an argument and he felt out like now they Henry David, because we are also made up of protons, we are also made up of electrons, we are also made up of neutrons, and we are telling that all these are waves, and why not apply for us also? When you are saying this object is a wave, that our electron is a wave, why not apply for us also? That was the question.
No. So see, my understanding of quantum mechanics, I'll tell you. So maybe my understanding of quantum mechanics is that is not a invalid question to ask. Every particle is a wave, but the wavelength of macroscopic particles is so small that quantum mechanics does not actually matter, right? The reason, so obviously, the wave corresponding to me as a particle in some sense is so completely decohered and so small that it does not affect anything at my macroscopic scale. So only when you go to microscopic scales does the wave nature of matter actually present itself to be measured in an experiment or observed in an experiment. That is the yeah.
ಏಲಿಯನ್ಸ್ ಮತ್ತು ಹಾರುವ ತಟ್ಟೆಗಳ ಬಗ್ಗೆ ನಿಮ್ಮ ಅನಿಸಿಕೆ ಅಭಿಪ್ರಾಯ ಏನು? ಏಲಿಯನ್ಸ್ ಮತ್ತು ಹಾರುವ
ಆಗ್ಲೇ ಅವ್ರು ಹೇಳಿದ್ರು ಇದುವರೆಗೆ ಇರುವಂತಹ ಎಲ್ಲ ಪುರಾವೆಗಳು ಕೂಡ ಅವು ಇಲ್ಲ, ಕಂಡದ್ದು ಸತ್ಯ ಅಲ್ಲ ಅಂತ ಹೇಳ್ತಾ ಇವೆ. ಅಂದ್ರೆ ನಾವು ಕಂಡಿರುವಂತಹದ್ದು ಭ್ರಮೆ ಇರಬಹುದು ಅಥವಾ ತಪ್ಪು ತಿಳುವಳಿಕೆ. ಮಾಧ್ಯಮ ಯಾವಾಗ್ಲೂ ಸತ್ಯ ಹೇಳುತ್ತೆ ಅಂತಂದ್ರೆ ಸರ್, ಮಾಧ್ಯಮಕ್ಕೆ ಎಲ್ಲಾನು ಜ್ಞಾನ ಇದೆ ಅಂತಾನು ಹೇಳಕ್ಕಾಗಲ್ಲ ಸರ್. ಸೊ ವಿಜ್ಞಾನದ ದೃಷ್ಟಿಯಿಂದ ವಿಜ್ಞಾನಿಗಳು ಕಂಡಿರೋದನ್ನ ಅದನ್ನ ಅವ್ರು ಹೇಳಿಲ್ಲ, ಮಾಧ್ಯಮದ ಬಗ್ಗೆ ನಾನು ಹೇಳಿದ್ದು. ಓಕೆ, ಅವ್ರಿಗೆ ಹೇಳ್ಬೇಕು. ಸೊ ವಿಜ್ಞಾನದ ದೃಷ್ಟಿಯಿಂದ ಇಂಥವನ್ನೆಲ್ಲ ಪರೀಕ್ಷೆ ಮಾಡಿದಾಗ ಎಲ್ಲೆಲ್ಲ ಪರೀಕ್ಷೆ ಮಾಡಿದ್ಯೋ ಅದೆಲ್ಲವೂ ಅದು ಸತ್ಯ ಅಲ್ಲ ಅಂತ ಗೊತ್ತಾಗ್ತದೆ. ನಮ್ಮದು ಬಂದಿತ್ತು ಅಲೆಯನ್ನು ಇಲ್ಲೇ ಇದ್ರ ಹತ್ರ, ಹುಣಸೂರ್ ಹತ್ರ, ಆವಾಗ ಈಗೆಲ್ಲೋ ಇನ್ನು ಗೊತ್ತಿಲ್ಲ.
So all examined claims of extraterrestrial visiting Earth have been shown not to be true. All examined ones. I'm not ruling out the possibility that actually there is an alien visitation on Earth. Could be, I don't know. Everything examined so far has not proven to be true. There's no evidence. There's no evidence so far. There's no public domain. That's all. Right? And one also has to be careful that in this particular domain, there are lots of conspiracy theories, especially with social media, right? And then one should not believe claims made by people without investigating a bit more than you would have before social media or the came, right? That's also something. There's a question at the back. Yeah. Yeah, so there are flyers outside. Yeah, that has the email at the end. That's the email to write. The people, the outreach team of our institute who are with the planetarium program are sitting here. Yashaswini and Amol, the Amol Vasha, the Yashaswini. They are working in Mysore or the University of Mysore campus. They've done some many kinds of events now in Mysore city and rural, in both in schools and colleges as well as with public in general as well. And so if you can email the Cosmos or Epoch at iit.in with who you are, what operation, what kind of thing you want, they'll get in touch with you. And did you reply? No, did you email and nobody replied? So you want to email and see. Now that they're here, I put them on the spot in front of YouTube, so they will have to reply first. Or you can talk to them now. After the meeting, you can catch them and talk to them and tell them liquid your organization, and we will see what we can do. So the idea, of course, so they've been doing a limited amount of outreach because we don't have our own campus. Yeah, once again. But once the campus comes up, of course, we'll have many more programs, and we'll have our own campus to have events in. But public night sky watches, public talks, visiting schools and colleges, schools visiting us, etc. All that has been going on for 2.5 years. Yeah.
How does your workday look like?
Oh, are your parents here? I get up quite late. Can I say that in front of her? I was going to get back. So I get up quite late. Scientists, general, I work in a government institution, right? Almost all science in India is government funded. So I manage to get up late, but then I also work very late. So I go to the institute. I can shatter all your conceptions of science by saying a lot of it is answering emails, but I won't, and answering meetings, but I won't do that. So I look after outreach and education. So I talk to schools and colleges, school students like yourself, college, people in public domain, organizations, associations, and try and form programs, right, where we go talk to them, engage with them in science and so on. If you look at scientists in my institute do research, some of them look at data. Some of them go to telescopes and observe some object they want to observe. Before that, they kind of figure out what is the research question they have. What is the question they want to find answers to, which nobody else knows the answers. Like for example, I said dark matter, dark energy, nobody knows what they are. Or they might say, okay, I have a particular galaxy, something is strange, I want to study what's in the center of the galaxy. I want to study what's happening around the black hole of the galaxy. I want to study how the gas forms new stars. Or I want to study how magnetic fields of the universe are placed, etc., right? So then you design an observation through a telescope. You apply for time, you get time, you go to the telescope, you look at the objects all night long or all day long with the radio telescope and so on, and then you come back to analyze the data very, very carefully, right? You can analyze the data very carefully using software, right? And then try and make conclusions which, based on the data you have, compare that with what is known, for example, and try and find new things, try and come up with new explanations, try and make new discoveries, and so on. Right? Or you can look at the theory. You can take a pen and paper, and you come and you can look at the theory like quantum mechanics, relativity, cosmology, etc., and try and at the places where we don't know answers to, like things about the Big Bang or so on, you try and come up with theories which will explain new observations while also explaining what everything else that is already known in science. So it's a lot of work which sometimes leads to dead ends, but suddenly sometimes you make a discovery or you make a breakthrough and then you're very happy for days on end. I would assume it's a very slightly whitewashed picture of a scientist day, but yes. Yeah.
I'm sorry, I think your answer actually, I am also a researcher, but I'm in the IPA. So if we dig deep into the data, right, then we will find some answer at some point of time. Otherwise, we may collect some more data. But in the field of astronomy, being like 95% of the things are unknown, like you mentioned, and 5% only you know. Like most of the work will be discoveries and the research, but was there any point where you guys were not, maybe through your experience, you were not able to find the answers to the data, and bias is one of the things researchers should not go into, right? Like, so when we don't have enough data, we unknowingly get biased actually. So is that happens in your
Sure, that happens. But then the training of a scientist, I would argue, is you're trained to recognize when there's not enough data, and therefore you're trained to figure out what is the thing you can actually state given the limited data you have and what you cannot state. So, for example, if you look at any scientific paper, you see any science paper, not just physics or astronomy, right? Biology, chemistry, engineering, any science paper, any measurement they'll give you will always have an error along, right? This is something very unique to science, right? No other branch of human endeavor this makes it a very important point to tell you what is the uncertainty or error in what I'm claiming. Many branches of human endeavor will claim there's no error in what I'm saying. What I'm saying is the truth, right? Science is not that. Science says any scientific measurement made or any scientific claim made has to come with its own uncertainty or error, which we estimate based on the uncertainties we think are there in the data, in my instrument, in my telescope, in my microscope, in the analysis method. So and therefore any number in any scientific paper will always come with plus or minus something, right? And if it is a number like 10 plus or minus 0.1, that means that 10 is reasonably accurate. If it is 10 plus or minus 2, then the 10 is even less accurate, right? And the uncertainty quantifies how much I can believe the number, right? So can I take it as 10 and not 11 and continue? Or can I say it's 10.1 and not 10.2 and continue? The error will tell you how much to believe or how much to take for granted that number and build things on top of it, right? And the goal of experimentalists, one of the goals of experimentalists is to make the error number smaller and smaller by devising better and better experiments, for example. Right? So uncertainty and error is inherent in science, right? And without any measurement made, there's no measurement made with like 100%. The only thing is the number of stars around which the Earth is going around, 1 plus or minus 0. That is zero uncertainty, right? But any actual measurement made will always have an error margin. Yeah.
Yeah. It's a simple question.
Sorry. Let him decide who answers.
No.
Okay, him on. Right.
There are many satellites revolving around the Earth. How do we prevent them from collision? Is there any predetermined trajectory?
So it's becoming a huge problem, right? And in fact, many satellites, including Indian satellites by ISRO, they change their orbits now and then to avoid space debris. So not just avoiding other satellites, that's not such a big problem for the big satellites, but space debris is left behind when a satellite explodes or when parts of it come off, whatever. And so many satellites, including the space station, including our own Indian satellites, periodically make orbital corrections by firing a rocket to avoid something they know might hit, right? And therefore, this whole idea of, as space debris is increasing, the idea of constantly monitoring smaller and smaller pieces of space junk so that we can protect the satellites is becoming very, very important. Even India, ISRO is now building a set of telescopes to keep monitoring that more, more accurately. So that is definitely an issue.
So from an environmental perspective, how do we treat space debris and how do we cope with space
Yeah.
debris?
I think the unfortunate history of humanity is wherever we go new, we first thing we do is pollute it, right? Whether it be the sea or the land or now the space itself, right? So now the new satellites being launched, there are now guidelines to make sure they don't, cause debris. Older ones, the turns around. So various space agencies, including India, are thinking of, some way of dealing with them. Either you have a huge net and track them, or you kind of, make them burn up, or some shoot at them to make them burn up. Whatever it is, right? And parallelly, new satellites being launched, you kind of ensure that it doesn't lead to space debris. The big ones, either after the end of the lifetime, either you deorbit them so that they can burn up the atmosphere. Now they're thinking of certain satellites where they can make them go out so that they can leave the Earth's atmosphere and go up instead. But space pollution is a big issue facing all space agencies. That's an issue. And it can have a very real impact. For example, when we have astronauts at the International Space Station, it's actually a matter of life and death sometimes, right? So yeah, it is an issue.
So do we need to know the trajectory of other?
Yes. So people track that very often, and all the major satellites end up making small maneuvers to avoid bigger space debris that was coming their way.
Citizen science project also on track. Right?
Yeah, I think that is. So it's become a big issue. That's what we do. We go pollute everywhere and then start worrying about solution. Unfortunately, that's been the history of humanity. Yeah.
How does one start in radio astronomy?
Radio astronomers. So radio astronomers either come through the BSc, MSc physics, and then do a PhD in astrophysics. But some of them also come from engineering background. If you have electronics engineering, that's also a way in, right? So both are possible. As a hobby, okay, that's an interesting question. Right, so amateur astronomy, is something which is very popular around the world, including India, and we have many of them in Bangalore, right? Where you have your own small telescope and you want to look at the sky and because you love it. It's fantastic, right? But radio astronomy in amateur level is relatively new in India. But you can do things. So, for example, NCRA, National Center for Radio Physics, has a radio physics lab there on the Tayuka, and on the website they have certain information on how to build your own small radio telescope, right? For example, many amateur astronomy organizations like Jyotirvidya Parisastha in Pune, or even the BAS and ABBA in Bangalore have made their own small radio telescopes. You can talk to them. But if you want to build your own, electronics engineers know much better than physics astronomers how to build small radio telescopes, right? But you can always, we can also talk to we have a telescope in Goregaon, it's a radio. So you put it in principle, through them, contact me, and then you can talk to them if you want. If you already have a design, you can bring it to our engineers, and they can help you better modify it and make it better. So on. Do look at the radio physics lab page, which is run by NCRA and Anuka jointly in Pune. They do have a lot of designs. And contact amateur astronomers groups in India which already have are doing it. They can use.
Are they available for buying? How much does it cost?
Radio telescopes for buying, not really. But you can buy a satellite dish and attach a satellite finder to it. But otherwise, you have to make it yourself. And electronics engineers will want to make it themselves. It's their passion, right? So you tell an electronics engineer buy it, they'll get very upset. They want to build it with their own hands, and there's a thrill in doing that by yourself. Yeah. Yeah.
So there's a news about James Webb Telescope found the galaxy farther than 14 billion years.
Okay.
Does that mean that Big Bang theory is?
Yeah. No, so it didn't find the galaxy farther than 40 billion years. What it did is that so we know the Big Bang happened 13.8 billion years ago, and then the universe expanded and cooled down, and it cooled down sufficiently to form gas, right, atoms and so on, and then they combined and got together with gravity, became galaxies. The gas in the galaxies then contracted, became stars, and so on and so forth. And we think we know the history of the universe well enough that we can predict roughly at what time these various things happen, right? So we have good models, we think, which tell you that after Big Bang, how long does it take roughly before a galaxy of a particular size can form. So galaxies, small galaxy, proto-galaxies form, and then they merge to become bigger proto-galaxies. They merge to become even bigger ones, right? This is called hierarchical galaxy structure formation. And therefore, our theory predicts as a probability, probabilistically, if you say a galaxy of particular size, roughly how long you need since the Big Bang for you to be able to form it. Okay, and James Webb Telescope is finding more and more examples of galaxies given their age, they are much bigger than our models allow it to be. So it seems like galaxies formed earlier than our models have been saying. And the models are constrained really well with a huge amount of data. And therefore, fact that they agree with so much data, but they don't agree with this one data is a problem. And therefore, there are like, many papers with various ways, solutions out of this issue of how to explain galaxies, big enough galaxies forming earlier than our models allow them to form. That is the issue. So open problem.
I have the present duty of thanking Dr. Niruj Ramanujam with a question that what is the probability of finding in Niruj Ramanujam elsewhere? So it's very probabilistic. I think we find only one unique person here speaking about astronomy and astrophysics so fluently for the last 2 hours. Oh,
You can never be sure.
so yeah, so that's it. And this is the second time he is speaking on this topic in my show, but it's different from the one that we heard some time back. And I think he has already given an indication that he would come back here and speak on something else also. And we will take it forward maybe after a few months. Okay. And on behalf of Kalasuruchi and Kutuhali Kannada, we are very thankful to Niruj Ramanujam for coming all the way from Bengaluru and staying with us and speaking about this. We have a small momentum as this one. How big? Come.
You are the one who's been running.
No. Wait. Please come. She asked a question.
Okay. Thank you.
Thank you all. Next month, same second Saturday, we will have another program. Probably there will be more, I would say not astronomical, but down to earth with music and other things. Thank you very much.
And all the planets are on Earth. And how it is Copernicus come around the system, say the sun, right? Center of the system, and everything.